Hey everybody, welcome to Calculus. Today we're going to be doing 4.5, analyzing the first and second derivatives algebraically. So the work that we're going to be doing today looks like this work right here. You'll be given a function, you'll need to find the second derivative, and then we'll do some analysis to figure out whether or not the original function is concave up, concave down, or if there's an inflection point. So there are some things that we'll look for. We'll make a sign chart, but the work that we're going to do today does look like this. Last time we analyzed functions using the graphs and features of those graphs. Well, now we're going to be using those same features, except we're going to be looking at them algebraically. So here is a reminder of the function analysis chart that we have built so far. These are the characteristics that we'll be looking for. So if you're asked a question about, hey, where does f have an inflection point, then you'll need to look for where f prime is changing increasing to decreasing, or grab a pen here, or the other way around, decreasing to increasing. Or then if you have the second derivative, you'll look for where it changes sign. Now, it's really hard to tell algebraically where a function is increasing and decreasing, so that way we always try to look for the change in sign. So we're looking to see where it's going to change positive to negative. So then I also wrote out some steps on how to find concavity algebraically. So the first thing we need to do, we know our overall goal is going to be to look at the sign of the second derivative, because if the second derivative is positive, so if f double prime is positive, then that means that f is concave up. If f double prime is negative, then that tells me that f is concave down. And then if we see a change from positive to negative, then we'll see an inflection point on f. So we do need to determine the sign of the second derivative, because that's going to help us determine concavity. So that is the big idea. I don't want that to get lost. I'm going to put this in a cloud. We really want to determine the sign of f double prime, or a second derivative. So the first thing you need to do is you need to find the second derivative. Then we're going to set it equal to 0, solve for x, or any other values that don't exist. And these are our critical values. You can create a sign chart for f double prime. So that sign chart is where you put those critical numbers on the sign chart, and then you test some intervals, and then you'll determine the sign of f double prime on each interval. And once again, if f double prime is positive, then that tells us that f is concave up on that interval. If f double prime is negative, that tells us f is concave down. If we see a change in sign, so if f double prime changes positive to negative, or from negative to positive back and forth, that tells me that f has an inflection point. So we're going to do all of this algebraically, and we will use page 113 in your notes packet. So if you still have that notes packet, you can look on page 113. This is printed there. We also talked about the first part a little bit last time. We defined an inflection point as a point where the graph changes concavity. So these are what we're looking for. To determine inflection points, we're going to find the critical values for the second derivative. Set f of x equal to 0. Then we're going to create a sign chart. And then inflection points happen when the sign changes from positive to negative, or negative to positive. All right, so I think we're ready. So we're going to do this one right here. Determine the intervals where f is concave up, concave down, and any inflection points. And then we'll talk about the function graphically. So the first thing I need to do is I need to find f double prime. have f. I'm going to find f prime first. So f prime would be 3x squared minus 6x. And then f double prime is 6x minus 6. Okay, step 2, just reminding you guys, set f double prime equal to 0 and solve for x, and then also find where f double prime does not exist. So let's set f double prime equal to 0 first and solve. So step 2, set f double prime equal to 0 and also find where f double prime does not exist. Okay, so set f double prime equal to 0. That means, I'm going to have 0 equals 6x minus 6. Add 6 to both sides. 6 equals 6x. And then I get x equals 1. Then I would also look to see where f double prime may not exist. Here, this f double prime right now is a linear function. If I were to graph this, it would be a line. So there isn't a place where f double prime would not exist because this is a line and a line would exist everywhere. However, if I ended up with something like f double prime equals maybe 3 over x, then you would look to wherever the denominator would be equal to 0. So f double prime for this specific function would not exist whenever the denominator would equal 0. So this part you have to worry about if f double prime has a denominator with x. But that's not the case here, so we don't have to worry about that. Okay, step 3 was to create a sign chart using the critical numbers, and then step 4, determine the sign of f double prime on each interval. Okay. Extend the page a little bit, and I want to view the whole page. There we go. New color. All right, so step 3, we're going to create a number line, so make a sign chart. So whenever I make a sign chart, I'm making a sign chart this time for f double prime because I'm looking for concavity. Put my critical number on there, 1. And then my sign chart goes from negative infinity to positive infinity. And then I'd pick numbers to test in the formula f double prime of x equals 6x minus 6 on either side. So let's say I pick, let me get a different color here. Let's say I pick the number 0 because 0 is less than 1. And then I pick the number 10. 10 is greater than 1. So if I substitute in 1 for x, if I put in 0 for x, I'll have 6 times 0 minus 6, which is negative. So that means that this eraser, there we go. So that means that this side is negative. And then if I substitute in 10, I'll have 6 times 10 minus 6. That would be 60 minus 6, which is positive. So if f double prime is positive, then if f double prime is negative, then f would be concave down from negative infinity to 1. And then f double prime would be positive from 1 to infinity. So if I'm trying to determine where f is concave up, I can say that f is concave up from negative infinity to 1, and we do use parentheses for concavity. because, oh wait, not concave up, not concave up, concave down. That's why I like to draw the picture there, concave down, D-O-W-N. From negative infinity to 1 because f is negative on that interval. And then f would be concave up from 1 to infinity because f double prime is positive on that interval. So I have an interval for concave down, interval for concave up. Now if I want to know if f has any inflection points, because that's also in the directions, I can say that f has an inflection point at x equals 1 because f double prime changes sign at x equals 1. Meaning that f double prime changes from being negative to positive at x equals 1. All right, so we're going to do another one of those. We'll do it a little bit faster this time. All right, so this time, same kind of question. Oh no, we need to look at the graph. Hold on, let me pause this and we'll look at the graph. Okay, so here is the graph of f. So this is the original function. We found that there was an inflection point at x equals 1, so that means right here, this is the inflection point. So this is the point, well, when x equals 1 exactly, if I can get there. No, I can't really get there exactly, but really close. But right at x equals 1 is where this graph changes from being concave down to concave up. Now, practically what that means, if you're a runner and you've ever had to run up a hill and there's a certain point of the hill that's really difficult to run up, that's the inflection point. That's where it changes from being concave down to concave, or the concavity would change. So that is happening right here. Now, if you're like, well, why don't I just graph these and look for it? Sometimes it's hard to find by the naked eye. Like sometimes it might be 1, sometimes it might be like 7/8. So it is hard. Sometimes it's hard to find with the naked eye. That's why we use calculus to help us. Also, I also grade your work whenever you submit stuff. So just be careful. Don't try to cheat the system here. Just do what I'm telling you to do. All right, let's do another one. It's going to be a little bit faster this time. Okay, so here we go. We've got f of x equals 8x cubed minus 2x to the 4th plus 3. So I need to find f double prime. But first I've got to find f prime. F prime, let's see, 8 times 3 is 24x squared minus 8x cubed plus 0. And then f double prime, 24 times 2 would be 48x. Minus 3 times 8 would be 24x squared. And then when I go to find my critical numbers, I need to set this equal to 0. And I don't have any places where there's a denominator in the x, so I don't have to worry about where this would not exist. So set it equal to 0, I have 48x minus 24x squared equals 0. I can factor out, looks like a 24x. And so then I would be left with 2 minus x here. So then if I set each factor equal to 0, 24x equals 0, 2 minus x equals 0, so then x would be 0, and add the x would equal 2. So these are my critical numbers. I'm going to make a sign chart. I'm going to put my critical numbers on that sign chart. 0 and 2. And last time I told you guys it was easier to check the sign chart whenever you use the factored form of the derivative. So we're analyzing the second derivative. It's going to make it easier for me to check the signs by using this factored form. So 24x times 2 minus x. Okay, so I'm going to test some numbers. Let's say I'm going to test the number maybe -1. A number between 0 and 2 would be 1. Number between 2 and infinity. Let's try 5 this time. Again, I'm only worried about signs. So for 24 times -1, that's a negative number. 2 minus -1 is a positive number. So a negative times a positive makes this whole thing negative. And then for the middle part, 24 times 1 is positive. 2 minus 1 is positive. Positive times a positive is positive. And then for 5, 24 times 5 is positive. 2 minus 5 is negative. So a positive times a negative is negative. So that means, let's see, if f double prime is negative, then that means that, let's find black here, f would be concave down from -infinity to 0, concave up from 0 to 2, and then concave down from 2 to infinity. So now let's write all this out. F is concave down from -infinity to 0, and then again from 2 to infinity, because f double prime is negative there. Then I can also say that f is concave up from 0 to 2 because f double prime is positive there. And this time there's a change in sign. See, a change from negative to positive, and then another change from positive to negative. So that tells me that f has 2 inflection points. F has 2 inflection points at, well, I guess I don't have to say how many because I'm getting ready to tell them. So let's just say f has inflection points at right here where there's a change from from negative to positive at x equals 0. And there's a change from positive to negative at x equals 2 because f double prime changes signs. So now we're going to graph. So let me graph it. So here's the graph. I did have to change the scale, so if you notice the scale is not your standard scale. But we did say that there were 2 inflection points. We said there was one at x equals 0, which is right here. So this graph is changing from being concave down to concave up, right at x equals 0. Then we also said there was another one at x equals 2, which is right here. So here's that inflection point as well. I probably, if I were looking at this on my own, I could probably guess that one, but the 2 didn't. That one looks like it's a little bit more difficult. I might have actually guessed this one if I had to guess it by eye, but it's really at x equals 2. Okay, so then let's look at some other ways you'll be asked to deal with concavity and inflection points. Just make sure I'm still recording here. Yep, okay. All right, so here's, let's see, some other questions you'll be asked. You'll be asked to do more than one thing. You'll be asked to determine where the function is concave down and also increasing. So you'll need to refer back to this chart again and say, okay, well, if I want to know where a function's increasing, then I need to know where f prime is positive. But then if I also want to know where the function's concave down, Then I need to know where the second derivative is negative. So see, algebraically, we cannot determine, it's really hard to determine increasing and decreasing, but algebraically, we can determine whether or not a function is positive or negative. So if you have to analyze something algebraically, we want to be able to tell signs, positive or negative. We just need to know which derivative we're going to use. So on this one, we have f, and I want to know where f is increasing. So if f is increasing, when f prime is positive. So I need to know that. That's one thing I need to know. The other thing I need to know is concavity. So f will be concave down whenever f double prime is negative. So I need to find the place where f prime is positive and f double prime is negative. So let's work on f prime first. Here's f. Let me find f prime. That would be negative 6x squared minus 60x minus 96. We will set this equal to 0 and solve. I'll pause so you don't have to watch that whole part. Okay, so I set it equal to 0, factored. I've got two critical numbers, x equals negative 8, x equals negative 2. I'm going to put those numbers on a number line. I'm going to test them. And f prime equals negative 6, x plus 8 times x plus 2. Negative 8, negative 2. All right, let's say I'm going to test negative 10, negative 5, and 0. All right, so if I test negative 10, negative 6 would be negative. Negative 10 plus 8 is negative. Negative 10 plus 2 is negative. So negative times negative times negative is negative. All right, and then negative, if I substitute in negative 5, negative 6 is negative. Negative 5 plus 8 is positive. Negative 5 plus 2 is negative. Negative times negative is positive. And then if I substitute in 0, I'll have a negative times a positive. 0 plus 8 is positive. 0 plus 2 is positive. So negative, positive, positive multiplies to be positive. All right, so f is, I'm looking for where f is increasing. So f would be increasing, let's find a highlighter here. Highlighter. So f would be increasing on that whole area. Okay, so now let's look about where f would be concave down. So to find I need to find f double prime. I'm going to look back right here to go to find f double prime. That would be negative 12x minus 60. I'm going to set this equal to 0. If I add 60 to both sides, I get 60 equals negative 12x. And 60 divided by negative 12 would be negative 5. So then I can put negative 5 on a number line. I'm going to substitute numbers into the second derivative, negative 12x minus 60. So let's say I'm going to substitute in 0 on the right, maybe negative 10 on the left. Okay, so negative 12 times negative 10 minus 60 is positive. And then if I substitute in 0, I'll have a negative. So then I'm looking for where f would be concave down, which would be when f double prime is negative. So I'm interested in highlighter. I'm interested in this part. Okay, so f double prime, and then I'm looking for where f is both increasing and concave down at the same time. So let's see. Let's look at let's make one big number line now. Well, okay. So here's f, right? Okay, so let's look at what's happening here. F is decreasing until -8 and then increasing. So I'll say f is decreasing and then increasing. Okay, then on the same number line, as far as concavity goes, till -5, f is concave up until we get to -5, and then concave down afterwards. So the question is asking me, when is f both increasing and concave down? Well, that would be where these two parts overlap. So that would be highlighter, this part. So everything from -5 till looks like infinity. Except I have a small mistake right here. So let's look back at that. So let's check that out again. Let's erase this part. Okay. Negative times positive times a positive is actually a negative. So let's fix that. This should be negative right here. Okay, so let's try this overall. Let's try this overall number line again. Okay, so let's make a chart for f again. Got my critical numbers, -8, -2. Okay, so now we can say, okay, so f would be decreasing until -8, decreasing, and then let's change color so it looks better, a little bit better, and then increasing until -2, and then decreasing again from -2 to infinity. Then let's look at concavity. F double prime was positive until -5. So let me put -5 right here. Okay, so F was concave up until we get to -5 right here. And then after that, F was concave down. So then I'm interested once again in where F is both increasing and concave down. So let me grab my highlighter. Increasing and concave down, where do those overlap? Increasing and concave down, looks like they overlap right here. So everywhere from -5 until -2. So I will say that F is increasing and concave down. From -5 to -2. Just be careful with those signs. They can get tricky sometimes for several people. Okay, So next, let's look at a couple of other types of questions you'll be asked. You'll be asked questions like this, where you're given f prime, and what conclusions can be drawn directly from the sign chart of the function of f when x equals 4. Well, let's see. If I were to make a sign chart, I would need critical numbers. So here's the factored form. They've already factored it for me. So if I set it equal to 0, don't let these exponents throw you off, because really all that means, if I expand it out, where's my eraser? All that means, if I expand it out, is that I'll just have this, x times x minus 4 3 times, and then x minus 2 twice. That's all that means. Now, if I set each factor equal to 0, from each one of these, I'm going to get an x equals 0. I'll just get twice. From all three of these, x equals 4, and then x equals 2 from those two. So I've got three critical numbers. Let's make a sign chart. And it might be helpful for you to, well, no, just kidding. 0, 2, 4. Okay, so let's make a sign chart. And we're going to make a sign chart with f prime. And let's substitute in -1, 1, 3, and even 5. All right, so if I substitute in -1 here, I'll have -1 squared. -1 squared is positive. -1 minus 4 is a negative number, but then a negative number cubed is negative again. And then -1 minus 2 is negative, but then a negative squared is positive. So positive times negative times positive is negative. Now let's try in between 0 and 2. Well, actually, we're really only concerned about what happens at 4. So let's jump over here. Let's substitute in 3. Let's substitute in the 3. So 3 squared is positive. 3 minus 4 is negative. A negative cubed is negative. And 3 minus 2 is negative, but negative squared is positive. So positive, positive is a negative number. Substitute in 5. 5 here, 5 here, 5 here. Let's see, 5 squared is positive. 5 minus 4 is positive, and that's cubed is positive. 5 minus 2 is positive. Positive cubed is positive. So I see a change in the derivative from negative to positive. This is f prime, by the way. So what happens to f when f prime changes from negative to positive? Well, let's go back to that chart. When f prime changes from negative to positive, then f would have a relative minimum. So I would come over here and I would say that f would have a relative minimum. That's what I would choose. Then another one, this one is interesting here. Okay, so this time they give me f double prime, and I'm going to make a conclusion from the sign chart. So if I were to set this equal to 0, looks like if I were to set this equal to 0 and solve, my critical numbers are going to be the opposite of what's in here. So it looks like -3 would be a critical number. +1 is a critical number. All right, so let's test -5, 0, and 2. And really, they're only interested in the interval from -3 to 1. So what's happening here? So let's test 0. So let's test 0. 2 is positive. 0 minus 1 is negative. 0 plus 3 is positive. And a positive cubed is still positive. So positive times negative times positive is negative. So let's see, given f double prime, what conclusion can be drawn directly from the sign chart about the graph of f prime on this interval? Let's see. Well, this is f double prime. What can I tell about the graph of f prime? Okay, so let's see. Well, I know that f double prime is negative, so let's go back to my chart. When f prime is negative, the derivative is decreasing. So I can say that f prime would be decreasing. So I would pick this part. Decreasing. And then lastly, this time I have the derivative. What can I tell from the sign chart? This one does get this one's really interesting. Okay, so first of all, let's find my critical numbers. No. Okay. Let's see, critical numbers. From this one, I would get 0, 8, -3, and -7. So I'll put all these on the number line. Okay. Then they're only asking me about what's happening at x equals -3. So I'm just going to look at this interval right here and see what's happening. Okay, so from -7 to -3, let's test the number -5. And then from -3 to 0, let's test -1. All right, so if I substitute in -5 for all of these, -5 cubed is negative. -5 minus 8 is negative, but you square it, it becomes positive. -5 plus 3 is negative, square it, it's positive again. -5 plus 7 is positive. Negative times all those positives is negative. Okay? Then from -3 to 0, if I test -1, so I'm going to put -1s here. -1 cubed is negative. -1 minus 8 is negative. Squared is positive. -1 plus 3 is positive. And then squared is positive again. And then -1 plus 7 is positive. So negative times all those positives is still negative. Okay. So what can I tell? What's happening at x equals -3? Well, f prime is negative. So I know that the function is decreasing, but that's not an option. It's not an option because they're asking me about what's happening at x equals -3. Okay, then if I go to my chart, to get a relative min or relative max, I need to see a change. I do know that there's a critical value at -3 because f prime was 0 there. But I don't see any of those happening. So what happens? Let's see what my choices are. It's not a relative minimum, not a relative maximum, because I don't see a change in the sign. Negative. No. Can't be a 0 because it's a 0 for f prime. It's not a 0 for f. So then inflection point would be if I were to be checking for f double prime. So then I need to pick that there is a horizontal tangent, but no relative extrema. So that means it's probably doing something like this. So where I would have a horizontal tangent at x equals -3, but no maximum or minimum. So pick that one. So that is this section. Hope it goes well, but if you do need